In the previous video, we had learned about standardization and covariance matrix. In this video, we'll be talking about the next steps. The next step involves eigenvector and eigenvalues. Let us first learn about them. An eigenvector is a non-zero vector that satisfies the equation, which is our A matrix, and thereafter we have our V vector should be equal to lambda, which is some scalar, and then again V is the eigenvector, right? So eigenvalues and eigenvectors are also known as respectively characteristic roots and characteristic vectors, or latent roots and latent vectors. You can find eigenvalues and eigenvectors by treating a matrix as a system of linear equations and solving for the values of the variables that make up the components of the eigenvector. So all these words won't be going into your mind that easily. That is why we'll be solving a problem. So let us take an example where our A matrix is 2, 1, and 1, 2. All right, so this is the matrix that we have, and we'll be finding the eigenvectors for these. So now applying this formula that we have, what it will be 2, 1, 1, 2, and we have to multiply it with the eigenvector. Let that be x1 and x2, and let that be equal to lambda and the same vector over here to multiply, right? So now if we equate this way, so 2 into x1, 1 into x2, so it will be 2x1 plus x2 will be equal to, so here what do we have? We have x1 and x2, right? So that is how it will be our lambda x1. And similarly, it will be x1 plus 2x2, and that will be equal to lambda x2, right? We are doing nothing, we are just doing the simple matrix multiplication that all of us know. Now we have to find the values of x1 and x2. So if we rearrange the values, then this becomes 2 minus lambda x1 plus, sorry for that, x2 is equal to 0. And similarly, it will be x1 plus 2 minus lambda x2 equals to 0. Right, so this is after the rearrangement that we have got. Now, if I just, what do you say, take this in the matrix form. So let me just, let us just keep that, right? And let's move on to this part and right here. Yeah. So now this can be represented in the form of 2 minus lambda 1, 1, 2 minus lambda. I hope that you are getting the stuff that we are doing over here. It's the simple x1 and x2 stuff that we have done and equated to 0, because all these equations are equating to 0. Now, if we multiply the stuff, and we try to find the value of lambda. So it will be lambda minus 3 and lambda minus 1 equals to 0. Okay, so now there are two values of lambda that we have to substitute so as to see. So one value lambda 1 can be 3 and lambda 2 can be 1, and we can find eigenvectors which correspond to these eigenvalues by plugging lambda back to the equations, right? The equations that we were solving over here. And let's try and do that. So if we have this equation, and if I add 2 minus 3 x1 plus x2, right? So equals to 0. So what that would be x1 equals to x2, because here I'm getting a minus sign, right? So there are infinite number of values of x1 which satisfies this equation, which is x1 is equal to x2. So only restriction is that not all the components in the eigenvector can equal to 0. So if x1 is 1, then x2 is 1, and an eigenvector corresponding to lambda equal to 3, we can get that as 1 comma 1. So let me just write that on the top. For lambda equal to 3, our eigenvector is 1 comma 1. Now let me substitute value 1 over here. So what that would be? That would be x1 equal to minus of x2, right? So in that case, for our lambda equal to 1, the vector that we'll be getting is 1 comma minus 1, right? So this is how our eigenvectors and eigen values are coming. So let me just move on to the next slide and also remove these drawings. Yeah. So eigenvectors and eigenvalues are the linear algebra concepts that we need to compute from the covariance matrix that we had discussed in the previous video in order to determine the principal components of the data. Now, principal components are new variables that are constructed as linear combinations or mixtures of the initial variables. Now, these combinations are done in such a way that the new variables are uncorrelated. The new variables herein being the principal component. And most of the information with the initial variables is squeezed or compressed into the first component. Now, geometrically speaking, principal components represent the directions of the data that explain the maximal amount of variance. That is to say that the line that captures most information of the data. The relationship between variance and information here is that larger the variance carried by a line, larger is the dispersion of the data points along it. And the larger the dispersion along a line, the more the information it has, right? To pull all this simply, just think of a principal component as a new axis that provides the best angle to see and evaluate the data. So the difference between the observations are better visible. Now, eigenvectors of the covariance matrix are actually the directions of the axis. Thus, if my data is here, so should the vector be in this direction or this direction, right? So, and eigenvalues are simply the coefficient attached to the eigenvectors. By what amount should it be rotated, right? So we can say that the eigenvector with the highest eigenvalue, that is something that we have to do in our next step. So once like we found out our eigenvectors, thereafter we are finding our principal components. The next step that we have to do is to arrange all these eigenvectors into descending order. Now, where the eigenvectors with the highest eigenvalue is the most significant and thus forms the first principal component. The principal components of lesser significance can thus be removed in order to reduce the dimensions of the data. Now, the last step is this, in which we are recasting the data along principal component axis. So, what do we do? It represents the maximum, most significant information of the data set. In order to replace the original data axis with the newly formed principal components, we simply multiply the transpose of the original data set by the transpose of the obtained feature vector that we just obtained earlier, right? So now let us look at the previous implementation and continue with that. So in our previous implementation, this was the covariance matrix that we were getting, right? Now we have to apply the eigenvectors here. So after applying the eigenvectors and the lambda, this is the matrix that we are getting. If you will just observe, we are subtracting it by the lambda. And these are the eigenvectors over here, right? And now if we just compute, I have already done the computation, so I'll help you with that. So uh, now the lambda value that you will get over here, it will come down to some 2.51. Okay. Now let me just clear and write it. So lambda value that we'll be getting over here is 2.51. And again, with all the equations that you will be getting over here, you will have to substitute. For example, after substituting in for V1, you will be getting the value of V1 as 0.161, right? Similarly, you can compute as per our previous discussion, you can compute all those values, and thereafter you can find the values of V2, V3 and V4. All right. So after finding the values, we sort the eigenvalues and their corresponding eigenvectors. Now, since the eigen values are already sorted in this case, we don't need to sort them, right? So here in this case, it is sorted. Thereafter, we pick k eigenvalues from and form a matrix of eigenvectors. So in our case, we had 4 in total. We picked 2 of them, and thereafter we are doing the last step as shown over here. We are multiplying with the transpose, and this is the matrix. We are multiplying it so as to give the answer, right? So this is the transform the original matrix, and thereafter on this matrix, after doing the dimensionality reduction, we can go ahead and perform any of the machine learning techniques so that it is helpful for us, and the bigger problem is solved into a smaller problem. So that is what PCA is.